My name is Amey Salvi, and I'm a PhD student at Indiana University, Indianapolis. This project was a collaboration with Shandong University, Renmin University, and Argonne National Lab. Today, I will be presenting a paper on Color Maker, a mixed initiative approach to creating accessible color maps. When used effectively, color can help communicate complex quantitative information and can be used in a variety of fields, such as the elevation of a location, the flux flow simulation in a printed circuit board, and in medical imaging to detect anomalies. Crucial data can be missed when appropriate color maps are not used. But there are also challenges to creating effective color maps. Designers have to balance various factors such as smoothness, perceptual uniformity, and color namability. While the visualization community has created tools to help visualization creators choose effective color maps, there is still scope for improvement. Visual tools like Color Brewer provides handcrafted color maps, but they have a limited set of options and do not offer the scope for modifications. CCC tool provides high design flexibility but can be challenging to use for novice users. This highlights the need for a color tool which automatically generates new color maps, including accessible designs for people with color vision deficiencies, and also offers high customizability options without the necessity of expert knowledge. So we introduced Color Maker, a mixed initiative design tool that balances designer creativity with computational support, allowing us to meet both designer preferences and establish perceptual guidelines for color use. So how does Color Maker work? So the interface allows designers to add the colors of their choice from the various color space options provided. We offer simple drag and drop interactions where users can specify the chosen colors and the algorithm optimizes the design iteratively. Users can also add multiple colors as well as move and stretch them as per their requirements. The interface gives color suggestions when users hover over the color map, which users can use to quickly add new colors. As you can see, the yellow color is added, which the algorithm accepts to generate a new solution. Similarly, users can use the color map curves provided to select a specific color by moving the beads in the color space. This gives more control to the user to adjust the color map. Users can also view a simulation of how the color maps would be viewed by someone with color vision deficiency. This color map can also be optimized by toggling on the Optimize for CVD option, which generates a colorblind friendly color map for the selected deficiency, while keeping the same user preferences. Let's take a deeper look at how the colors can be selected by the user. The users can simply drag and drop their preferred colors from the color spaces which are provided onto the preference shelf given below. Once added, they can move, stretch, as well as remove colors as per their convenience. To remove a color, they simply have to drag the color out of the preference shelf. So let's see how the optimization works. We assume that the sampling points are equally spaced in the color space, which we refer to as control points. The color map is optimized based on the luminance profile selected by the user, which is used as a hard constraint. Users have the option to choose between multiple luminance profiles like linear, divergent, and wave style design. The goal of the optimization is to determine an optimal curve in the lab space that meets both designer preferences and perceptual standards. We use simulated annealing as the algorithm to optimize our solution. The algorithm starts with a randomized solution with a random set of colors chosen from the CIE lab space. The A and B components of the color are randomized while the luminance is set based on the chosen luminance profile. The solution is evaluated using the cost function and set as the best solution. In the next iteration, the A and B values of the color are perturbed by a small amount. The algorithm iteratively evolves the solution at each step picking the better solution. This process is repeated for the number of iterations selected, which is controllable by the user through a slider provided in the interface, finally reaching the optimized design. Here we can see a walkthrough of the optimization process. Notice how the solution is completely random at the beginning, and then with every progressive iteration, it starts converging into an optimal solution, finally giving us a smooth and uniform color map. We also incorporate user preferences by introducing bias in the algorithm towards the colors chosen by the user. The algorithm favors chromatic components specified by the user. This bias follows a Gaussian, affecting corresponding control points depending on how close they are to the user-preferred colors. A more stretched color, like the blue in this example, will spread over a wider set of control points, but will have a more diffused bias. Whereas a narrower block, like the red here, will provide a more focused bias to the control points corresponding to it. Now, once the colors are selected, the algorithm uses a cost function to calculate a penalty score for every solution or color map. The objective is to find the solution that exhibits the minimum cost. We balance three factors in the color map generation process: perceptual uniformity, smoothness, and color vision deficiency. Perceptual uniformity implies that control points are at perceptually equal distances from each other. As you can see from the example, the non-uniform color map has control points at varying distances as compared to the uniform color map. Our cost function penalizes the color map for the deficiencies in uniformity. The next parameter is smoothness, where we plot the colors in the color space. A smoother color map has a smooth transition without any abrupt changes, as opposed to a less smooth color map, which has sharp bends in the curve, which leads to bands of colors being formed. Our cost function penalizes this lack of smoothness in the color map. The final parameter is color vision deficiency, where we penalize the solution for being not safe for people with color blindness. We evaluate the color discriminability of the CVD simulated color map, and for every pair of colors, if the distance falls below a certain threshold, which implies that a CVD viewer would be confused by those pair of colors, we exert a penalty on it. Once the color map is generated, users can quickly make changes by selecting the suggested colors. A similar result can also be achieved by adjusting the color curves, which provides more control to the user. We conducted two evaluations to test the effectiveness of ColorMaker. First, we compared the color maps generated by ColorMaker with established popular color maps, which were chosen from reputable sources. We compared them with a large sample of generated color maps using ColorMaker. We analyzed the perceptual characteristics, testing for sequential and diverging scales for low as well as high number of hues. Here we will see the results for sequential color maps. From the results, we can see that perceptual uniformity for ColorMaker was noticeably better than the benchmarks. It's important to mention that lower score is better, implying smaller deviation from the expected color distance. For smoothness, for limited hues, the color maps produced by ColorMaker mostly overlap with the benchmarks, with blues appearing to be more smoother. As the constraint is relaxed, thereby allowing more hue variations, the color maps generated seem to be less smooth, indicating our algorithm favoring more vibrant color maps. For CVD, we plot discriminability as observed by a viewer with Deuter anomaly, which is the most common condition found. When the CVD optimization is enabled, ColorMaker generates designs that are sufficiently discriminable by a person with color blindness. In summary, the designs produced by ColorMaker produces a diverse set of solutions with perceptual characteristics similar to well-known designs. We also conducted a user study with visualization practitioners with varying levels of expertise. We recruited 13 participants from varying fields. The study comprised of 3 tasks: asking the users to generate existing designs based on specific dataset provided, and also creating custom color maps without any form of restriction. Overall, participants expressed satisfaction at the color map generation prowess of color map, saying it produced effective color maps. Most participants found ColorMaker's interface and color preference model to be very intuitive, while also allowing for quick and easy changes. Of the 13, 10 participants used the CVD option and commented on the usefulness of the feature. There are also a few suggestions for improvement to the existing model, with addition of sharper contours if needed, as well as a drafting mode for quicker iterations. To conclude, we introduced Color Maker, a mixed initiative approach for automatic generation of color map. Our tool offers intuitive selection of user preferences and customizations, and our evaluations confirm that this approach produces a diverse set of high-quality maps on par with existing designs. The tool is implemented as an open-source web-accessible tool available at colormaker.org. Thank you.